This week we will cover the last two major clades of dinosaurs, the Marginocephalia and the Ornithopoda. Marginocephalians were the last group of dinosaurs to appear in the fossil record, with the oldest representatives showing up in the very late Jurassic. Marginocephalia is divided into two major clades, the bipedal, dome-headed Pachycephalosaurs and the mostly quadrupedal ceratopsians, with their noteworthy skull frills. Pachycephalosaurs do not appear in the fossil record until the middle of the Cretaceous, and are officially the last dinosaurian suborder to have evolved, and hence the shortest lived. Like all ornithischian dinosaurs, Pachycephalosaurs seem to have been almost exclusively herbivorous. Their broad hips and rib cages show that they had large hindgut regions for digesting difficult-to-process plant matter. The most noticeably unique feature of Pachycephalosaur anatomy is probably their dome-shaped skulls. It has been suggested that these skulls were used similarly to how rams use their thick curled horns for headbutting. This may have been a defensive measure, a means of intraspecific competition, or both. We can tell that the bone in the dome-shaped skull was not just thickened to deal with the forces of impact, but its internal structure was exceptionally dense for bone tissue, and bone fibers were oriented in a columnar fashion, perpendicular to the surface of the skull. Even at the microscopic tissue level, these skulls seem to have been braced for impact. The fossil record of Pachycephalosaurs is quite poor compared to that of other dinosaur clades. In addition to being a short-lived suborder and not broadly distributed, the Pachycephalosauria seems to have had a natural habitat that was not conducive to fossilization. It seems likely that they inhabited upland regions, perhaps especially forests or mountainous regions where erosion is more common than sedimentary deposition. Their skulls could have doubled as helmets for running through forests with reckless abandon, glancing off any tree stumps that may be in the way, as they safely evade large predators. It may have protected them in falls if they misjudged a step while climbing steep, rocky terrain. It also seems likely that their fossil record has yet to be expanded with further discoveries. Pachycephalosaurs look at least superficially like primitive ceratopsians that had not quite become obligate quadrupeds. Dinosaurs like Yinlong and Psittacosaurus went extinct in the early Cretaceous, leaving a substantial gap in the fossil record between Pachycephalosaurs and other bipedal marginocephalians. As with the lengthening of the sauropod neck mandating dropping to all fours in that group of dinosaurs, expanding the ceratopsian frill also rendered ceratopsians obligate quadrupeds. We call these more derived, big-headed quadrupedal ceratopsians the Neoceratopsia. It is these advanced forms that managed to migrate from Asia to North America, where they proliferated and diversified throughout the Cretaceous. In Asia, ceratopsians went extinct, having their low-browsing niche filled by other dinosaurs. Based largely on the ways their skulls are built, Neoceratopsians appear to have evolutionarily split into two clades shortly after arriving in North America, the Centrosaurinae and the Chasmosaurinae. Centrosaurines include ceratopsians that tended to have much shorter brow horns compared to chasmosaurine ceratopsians. Chasmosaurines also tended to have longer frills proportional to the rest of the skull. These Neoceratopsians had, proportionally or otherwise, the largest skulls of any terrestrial vertebrates. The list of potential uses for these huge skulls is long. It seems likely they would have been useful for intraspecific identification and visual communication. They may have intimidated both potential rivals and potential predators. Ceratopsian skulls were not just long in the frill, but in front of the eyes as well. This horse-face shape likely helped them reach low-growing plants to eat without having to bend their relatively inflexible necks or arms to bring their mouths closer to the ground. The frill would have served as a counterbalance to these long faces, making it easier to pull up on a mouthful of plants once the beak at the front of the skull had latched onto it. And finally, we've arrived at the most persistent and widespread ornithischian dinosaurs, the Ornithopoda. They, like theropods, have been found on every continent, including Antarctica. Ornithopods seem to have ranged from bipedal to facultative quadrupeds, but never was there an ornithopod that was an obligate quadruped. Rather than needing to drop to all fours when they got massive, ornithopods supported their mass passively, with strong tendons that paralleled one another and spanned across neural arches in the back and tail. These tendons were ossified, meaning they were calcified and hardened, just like bone. So these ossified tendons rendered the backs and tails of ornithopod dinosaurs almost completely rigid. There are two major clades of ornithopod dinosaurs, the Iguanodontidae and the Hadrosauridae. You've probably heard of Iguanodon, as it is one of the first dinosaurs discovered and named, even before the word dinosaur was coined. Probably the most unique anatomical feature of iguanodontids is in their hands. Their three middle fingers terminated in hoof-like unguals. Their pinky fingers, digit number 5, were opposable, like our thumbs. Their thumbs, however, were capped with sharp, thick spikes that functioned as permanently mounted shanks on each hand, ready to stab would-be predators in the neck or other exposed soft spots. One feature all ornithopods had, starting with even their most primitive forms, was a very efficient chewing system. Their maxillae, or upper jaw bones, flexed with each motion as ornithopods moved their jaws. This phenomenon, called pleurokinesis, allowed them to grind their upper and lower teeth across whatever they were chewing by simply moving their jaws in a scissor motion. As mammals, our skulls are rigid, so to use our molars for grinding food, we have to gyrate our jaws, which is much less efficient. If you are a fan of beef jerky, you're probably aware of how quickly your jaw muscles can get worn out after working them out on a tough hunk of meat. It is this pleurokinetic efficiency that allows ornithopods to effectively chew their food, preparing it for simple digestion after it was swallowed. These dinosaurs had little need for huge fermentation vat stomachs or gastroliths, since they were able to mechanically process plant material between their teeth, breaking open cellulose cell walls manually. The apex of vertebrate chewing capabilities was probably found in the advanced hadrosaurs, or duck-billed dinosaurs, as they are sometimes called. In addition to pleurokinetic skulls, they progressively developed larger and more complex dental batteries. These teeth in the cheek region were tightly packed into a single pavement, and the way the tooth rows erupted, multiple rows of teeth were exposed at once. All of these teeth were tightly spaced and ground flat by frequent chewing to form a long and broad pair of pavements or dental batteries that skidded laterally across one another with each opening and closing motion of the jaws as these hadrosaurs chewed. Hadrosaurs themselves diverged into two clades, the crested lambeosaurines and the uncrested hadrosaurines. Lambeosaurine head crests are very interesting structures. They varied in size and shape from one species to the next, and possibly between genders and age groups within the same species. Sexual dimorphism is the term for the different appearances male and female members of the same species might develop. These head crests also were hollow, as this is where the nasal passages traveled from the nostrils to the pharynx and the throat. The tone and timbre of vocalizations of lambeosaurine hadrosaurs were probably enhanced by their head crests. If you are familiar at all with how trombones work, you will have an easy time understanding how the pitch of a hadrosaur's bleat was likely determined by the length of its crest, and why the shape and length of the crest affect how the sound resonates. Longer crests produce lower-pitched sounds, which can be advantageous for a couple of reasons. Low-frequency sound waves travel farther than high-frequency sound waves at the same volume. It is also harder to pinpoint the source of a low-frequency tone than higher-frequency tones. Obviously, greater range is important for communicating across greater distances and over the other sounds of the Cretaceous landscape. Being harder to triangulate the source of such alerts or announcements is also important for helping to avoid drawing predators directly to the herd. It is likely that such unique structures serve more than just the purpose of making sounds, though. In addition to resonating the air within, these crests may also have helped condition that air for temperature or particulate removal and/or humidity. Air on the way out of the body may have had moisture culled from it through condensation as it passed through these long tubal sinuses. Air on the way in could have been warmed before passing into the body on cool mornings and cooled before passing into the body on hot afternoons. Dust and sandstorms might have been regular seasonal occurrence in parts of Cretaceous North America, so the added length and severe curve of the sinuses at the distal apex of the crest might have facilitated an efficient air-scrubbing dust removal system. The design also reminds me of the mechanical water cannons in large, dancing water fountains. If you've ever watched elephants mist themselves by blasting water from their trunks on a hot day, it is easy to imagine the cloud of cool vapor a herd of Parasaurolophus could have generated. These incredibly long crests may have also had something to do with feeding on aquatic vegetation. A crested hadrosaur would have an easier time keeping water out of its lungs while dipping its head into and out of the water. The sinuses inside the crest would not serve to trap air for breathing in this case, but to trap water at the front, preventing it from getting into the backside of the crest, where it could pass down into the lungs. They would not have had any sort of snorkeling functionality, since the nostrils are at the front of the dinosaur's face and not at the end of the crest. The parental care model we discussed with sauropods seems to have been quite the opposite of what we see in hadrosaurids. This investment in the next generation is a relatively rare thing for reptiles. Primitively, as the model we discussed with sauropods, reptiles are what we would call R-selected organisms. They produce many offspring, and there is relatively little parental investment. Most of these offspring will never make it to adulthood and are essentially fodder for predators, effectively a population cushion to keep the more fit individuals in the gene pool long enough to produce the next generation. The opposite of R selection is K selection, little r and big or capital K. K-selected species are like us. We invest greatly in the next generation, expecting most of our offspring to survive to adulthood. Judging from the degree of parental care, at least apparent in the fossil nest of some ornithopods, hadrosaurs in particular, we can see that these dinosaurs were more aligned with the K-selection model. Their hatchlings were altricial rather than precocious, and appear to have spent extensive amounts of time in the nest after hatching. Adults would have to have supplied these hatchlings with food until they could make it on their own.